In this video, we shall look at a few review problems associated with two crucial concepts, namely work and energy, and the roles they play in rotation. So let's get to the problems. Problem 1. A string is wrapped several times around the rim of a small hoop that is given here in blue, with radius 0.1 meter and mass 150 grams. The free end of the string is held in place, that is the free end being held in place, and the hoop is released from rest as shown below. Find the tension in the string as the hoop descends as the string unwinds. So let's do part A first. First, let's quickly sketch the free body diagram. So you have tension going that way, and then you have this weight of this hoop, let's call it mg, and because the hoop is descending, the center of mass of the hoop would have an acceleration, let's call it a. From this free body diagram, we can immediately write the Newton's second law as mg minus tension is mass times acceleration. So that's equation 1. We can obtain another equation by analyzing the torque that is being exerted on this hoop by this tension. And that torque by that tension is given by that tension times the moment arm. In this case, the magnitude of the moment arm is just the radius of that hoop. So tension times the radius equals the moment of inertia of that hoop times the angular acceleration of that hoop, which is now equation 2. Note that this is tau. That refers to the torque on this hoop due to that tension. Now let's elaborate a little bit this equation number 2. So tension times the radius of the hoop, the moment of inertia of this hoop about its center is given by the mass of the hoop times the radius squared. And alpha is the angular acceleration of the hoop, which can be expressed in terms of that tangential acceleration of the hoop in a following manner. It's just a tangential acceleration over the radius of the hoop. So let's write that here. We see that this r goes away and this r cancels that one. So we get an equation that states tension equals m times a. Now placing m times a as tension here, you will get mg minus tension equals tension, which then yields tension as half of the weight of the hoop. So if we know the mass of the hoop as 150 grams, then the tension in that string as the hoop descends is half times 0.15, I'm converting grams into kg, times gravitational acceleration, and that is 0.736 newtons. And that's the answer for part A. Now let's look at part B. We want to determine the angular speed of the rotating hoop after it descends 0.5 meters. So let's assume that that position is here. So that distance right there is 0.5 meters. So this is position 1 and this is position 2. We are going to apply principle of conservation of energy here. So the kinetic energy at position 1 plus the gravitational potential energy at position 1 equals the kinetic energy at position 2 plus the gravitational potential energy at position 2. Now we have the freedom of choosing the gravitational potential energy to be 0 at some point. So I'm going to choose that level to be the 0 joule energy for the gravitational potential energy. Since the hoop is released from rest, so that means K1 is 0, namely the kinetic energy there is 0. The gravitational potential energy at point 1 is given by the mass, which is 0.15 times gravity times this height, because we have chosen this height or that level to be the 0 joule level. So the height is 0.5 meter. Kinetic energy at this point, namely point 2, is given by half times the moment of inertia about that contact point, not about the central point, but about the contact point, times the square of the angular speed plus u2. u2 is 0 because the potential energy there is 0. Now let's calculate I. I is the moment of inertia about that axis, not about the central axis. So using the parallel axis theorem, the moment of inertia about the rim is the moment of inertia through the center, which is the mass times the square of the radius, plus the mass times the square of the distance between the old axis that passes through the center of mass and the new axis. In this case is r, so r squared. R is the radius of the hoop, so together it is 2mr squared. Placing this information in here, we get 0.15, that is the mass, g 0.5 equals half times 2 is 1, m again is 0.15, r squared, omega squared. So you see the 0.15, the mass that is, will just get cancelled. And we can solve for the omega. It is just the square root g times 0.5 over the radius of the hoop. Note that we have already taken the square root, so square root of a square is just r. We are given the radius. Radius is 0.1 meter. So substituting that 0.1 meter here, we can calculate the angular speed of the rotating hoop at that point, which is 22.1 radian per second. And that solves the problem. Problem 2. Find the work that is needed for the system below to rotate about the axis shown. The axis is that point there, and the axis coming out of the plane, from rest to an angular speed of 6 radian per second. We know that work is given by the change in kinetic energy. So final kinetic energy, in this case kinetic energy of rotation, minus the initial kinetic energy of rotation. Now this is starting from rest, so that is 0. So work is just the final kinetic energy of rotation. So to do that, you need to know the moment of inertia of that system about that axis times the angular speed and square that. So the angular speed is known at 6 radian per second. So that means we just have to calculate the moment of inertia about that axis. The moment of inertia about that yellow axis can be calculated in a following manner. These are point masses, so you should have 3 terms. So let's do the first contribution. Let's begin with the 0.4 kg mass on the left. So the moment of inertia from its contribution is its mass, 0.4 kg, times the perpendicular distance squared to the axis of rotation. Now we have to convert the distance to meter, so 0.3 meter, and don't forget to square it. Now the contribution from the right, 0.4 kg mass, 0.4 kg, the distance is equal, 30 cm, to the axis of rotation, so 0.3 meter. And the final contribution is from the 0.2 kg on top. The perpendicular distance between that 0.2 kg mass and the axis of rotation, let's call it L. And L can be computed, L square can be computed using the Pythagoras theorem. It is just the hypotenuse, 0.6 meters squared, minus 0.3 squared. So the last contribution is 0.2 times the L squared that we have computed here. So putting this information in here and substituting 6 radian per second for omega, we can calculate the work that is needed, which is 2.3 joules. And that solves the problem. Problem 3. A thin uniform rod has a length of 2.2 meters, so that is this rod. It is pivoted about a pin as shown below, so the pin is right there. The axis of rotation is coming out of the plane. It is released from rest at an angle of 30 degrees above the horizontal as shown. So at this point, the angular speed is 0 radian per second. What is the angular speed of the rod as it passes through the horizontal position, namely that position as it comes down like that? So we have to use the principle of conservation of energy here. So let's call that position, the starting position, as position 1 and this horizontal position as position 2. So the energy at position 1 is given by the kinetic energy at position 1 plus the potential or the gravitational potential energy at position 1. At position 2, the kinetic energy is K2 and the potential energy there is U2. According to the principle of conservation of mechanical energy, the sum must be conserved. The sum is the same. At position 1, the angular speed is 0, so that goes away. Also, we can set this level to be 0 joule level for gravitational potential energy. So that means gravitational potential energy at position 2 is 0, so that goes away as well. So let's calculate U1. U1 is gravitational potential energy of the rod. Now the rod is uniform. That means the center of mass is exactly in the middle. That is at 1.1 meter mark from the axis of rotation. The vertical distance from the 0 joule mark of this center of mass is represented by that height. So we can calculate what that height is from simple trigonometry. So this is h, this is 1.1, and this is 30 degrees. So you see that h is 1.1 times sine 30 degrees. So gravitational potential energy when the rod is at position 1 is given by its mass times gravitational acceleration times h, which is 1.1 times sine 30 degrees. Now what about K2? What is the kinetic energy of this rod as it passes through the horizontal position? It's given by half the moment of inertia of this rod about the axis of rotation times omega squared, where omega is the angular speed at position 2. Let's calculate the moment of inertia of this rod about one of its end. It's given by the parallel axis theorem again. It's moment of inertia through its center of mass plus the mass of that rod times the square of the distance between the axis of rotation passing through the center of mass and the axis of rotation about which the moment of inertia is to be calculated. So the distance here is 1.1, so 1.1, and don't forget to square that. The moment of inertia of a thin uniform rod about an axis passing through the center of mass is given by 1/12 times the mass times the length of that rod. In this case, it's 2.2 meter squared. And plus the second term, mass times 1.1 squared. Now substituting this information in here, we can calculate omega. Note that the right hand side is half omega squared. I is just m/12, 2.2 squared, that's the first term, plus m 1.1 squared. The m cancels, and you can determine omega, which is found to be 2.6 radian per second. And that solves the problem. Thanks for watching.